All right, Michael, we kind of screwed up. We started the lesson and we forgot about you for a second. Let me give you a quick review here.
Don't forget about the demonstration,
Okay.
Mr. K.
Oh, well, the demonstration can't be captured on a smartboard screen.
I'm offended.
All right, Michael, here we go. Review. Acceleration is a vector value. If we change an object's speed or direction, it's going to be accelerated. Where was I? If gravity if the sun were to completely blow up, then 8 minutes later, when the gravity wave passed us, Earth would continue at a tangent to the path to its circular orbit. Okay, so if it would just in this direction that you can see right here, that's where we would continue if the sun just disappeared. Now, these next three circles, don't worry about it. It's just a proof to show that as the change in velocities get closer and closer to a small time interval, the change in velocity, which means its actual acceleration of the object that's changing, is directed towards the center of the circle. Okay? It's not directed down or up. It's in order to keep an object moving in a circular path, the force it's applied has to be pushed towards the middle of the circle. Okay, you're caught up. Great, that was the last 15 minutes. All right, so now what we're doing is the proof. We haven't started the proof. I'm just about to introduce what these arrows on the screen mean. All right, so we've got two different instantaneous velocities. I could have drawn these anywhere, but it works out nicer if they're right-angled triangles when we end up doing this this proof.
Is that an R of the this one center? Yeah.
It's an R.
Those are R's?
Yeah, those are radii. No. So we've got radius 1, radius 2, velocity 1, velocity 2. Alright. I got my handy dandy proof here.
Why do I use the same color? I have all the different colors.
Okay, I'm actually going to do this proof. I don't like the way I've set it up here. I'm going to do this proof on a blank smartboard sheet. So I'm going to be going back and forth from this diagram to a blank sheet.
You want us to write this on the blank sheet or just kind of follow along?
On a blank sheet would probably be best. You should have it. Pick it up. Where is it?
Maybe.
Alright, so since our object's speed is constant, the magnitude of the two velocity vectors is the same. Might as well do this in like different postulates, like 1, 2. And the magnitude of the radius vector is the same as well because it's a circular path. And we know that the definition of a circle is the point, or a set of points which are equidistant to one point. Okay, there's the triangle that represents the change in displacement and velocity between those two vectors that I drew. Okay, for the people just coming back, pause this for a second. This is an important part of this proof. Since R1 is perpendicular to V1, that's the definition of a tangent to a circle, and R2 is perpendicular to V2, what type of triangles are my vector or my velocity triangle and my radius triangle? What types of triangles are they? They are right triangles in this case, but if R1 and or if V1 and V2 were not 90 degrees to each other, they wouldn't be. They are isosceles. More general, look at how they relate to each other. Okay, if R1 and if R's are perpendicular to the V's, you learn it in grade 10 before you do trig. You do a bunch of ratios based on what type of triangles? Similar triangles. Good. Okay. Oh, by angle, angle, side, or by side, 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 or whatever. Is that what you're talking about, the proof? What's that? Oh, perpendicular. It's a perpendicular symbol. Yeah. All right, so this is important. This is a jumping off point for the rest of the proof here. Okay, so we can use ratios now between V's and R's. Okay, so because of that property that they're similar, this, guys, I'm not gonna lie, this is a long proof. Okay, so we're about halfway done here.
I ran out of colors.
Sorry.
I still
As a consequence of the similarity of the triangles. Okay, so now we can express equivalent ratios of the sides. do you want delta V by itself? Remember, all of this is just talking about the magnitudes of the vectors. We're not talking about directions yet. Okay, the proof for the direction was the last, those 3 circles I did on the previous page, showing that the directions of acceleration is going to be pointed in towards a circle, the middle of a circle. Okay, this is all about magnitudes of the acceleration. And there is, in this proof, there is a definite difference between delta R and between delta V and V. Based on, based on the triangle, sorry. Okay, V is the magnitude of either V2 or V1. R is the magnitude of either R1 or R2, but delta R and delta V are definitely different vectors. Okay, let's keep going. You guys caught up? Step 7. Oh, the t doesn't need a magnitude because it's not, sorry. The t is not a vector. The limit as t approaches 0, okay? Unlike every other kinematics equation that we've talked about where acceleration is constant, when we do a circular motion, the magnitude of acceleration is constant, but its direction is not constant. Its direction is always pointing towards, from the object towards the middle of the circle. So we have to say that the instantaneous acceleration, if we define it as such, is the limit as the time frame approaches very, very, very small as delta V divided by delta t. And where do we go from there? Yeah, so now we sub in the previous equation. What's that? The limit of the as the change in time approaches 0 but doesn't quite get to 0, because then we'd have an infinite situation. Right? The acceleration is of a very, very small change in time, like the millisecond time frame, or even smaller. The change in the velocity. So if we do v2 minus v1, just like we had back here, okay? As t got really, really small, the change in velocity vector pointed towards the middle of the circle. The magnitude of the acceleration is going to become the magnitude of this vector divided by the change in time. Okay. Now this vector is going to get really, really small, but time is going to get really, really small as well, so it's going to work out to an actual constant value. Now, there's a lot of calculus behind this, but this proof avoids the calculus, which is why it's nice. Okay, it's over a small time frame. Let's do So subbing in delta V equals V delta R over R. Centripetal acceleration is the limit as t approaches 0 of V delta R over R delta T. And things are going to starting in this next step, things start to simplify.
The delta T doesn't need to be boxed.
That's right. The delta T does not need to be in boxes. Or else means magnitude of the vector. Okay, so we're on step 8. This is the longest proof we do all year. Promise. Just like we could define instantaneous acceleration as the limit as t approaches 0 of delta v over delta t, if we take the change in position divided by the change in time, then we get the instantaneous velocity, which could be v1 or v2 from our original vectors. So the neat thing about properties of limits is you can break them up, okay? So I can say that this is the limit of the property of t equals 0 of v over r times the property, or times the limit as t equals 0 of r over delta t. So the limit as t equals 0 of r over delta t is just v, okay? Our instantaneous velocity, which we've been calling v at this point. So what we're left with, we're going to sub out r over delta t from step 7 and replace it with v. Things are starting to start to get simpler here. No, that's fine. So since we did enough substitutions to eliminate the t term in the right-hand side of the equation, we don't need the limit as t approaches 0 anymore. And we're just left with the magnitude of the centripetal acceleration as v squared over r. And we don't need to show the magnitude brackets every time. Let's do it once with magnitude brackets, just so you remember. And then we'll just express it without magnitude brackets. Well, yeah, great. That's great, that's great, that's great. Okay. That's the end of the proof. Let's just note that this is magnitude only. It's a hell of a lot of work to get v squared over r. Okay, and back to the note. So the formal term given to circular acceleration is centripetal acceleration. And I guess we should kind of show what the two different terms are. Let's do an example from the textbook, shall we? Okay, let's go to page 124, number 4. And now we get to see that there's 2 other different variations of this equation. Yeah, it's gonna be awesome because you can do v squared over r, or you can use frequency, or you can use period. Yeah, it's gonna be neat. So you can use how fast it's rotating, and we're gonna see how we can get those these other equations. A wheel of radius r rotates, making f revolutions per second, f being frequency in hertz. The quantity f is known as the frequency of motion. Show that 1 over f is the time to complete 1 revolution, called the period of motion. And show that the centripetal of acceleration at the point at the rim of a wheel is 4 pi squared r f squared. Doesn't seem like a big task at all. Here we go. This is more of a proof than an example, but it works anyways. If velocity is distance divided by time, then how far has the object moved in that circular path to go once around the circle? No distance. We're doing speed, not velocity. Circumference, which is 2 pi r, not squared. Okay, circumference is pi r squared. So we're going to sub in we want that delta t squared. Yeah. Because velocity is delta d over delta t, and we're doing v squared. Okay, so the delta t is squared as well in the denominator.
So wait, are we putting the square on the r or on the other for the numerator?
Oh, thank you. Square goes outside the bracket.
I no problem.
Okay. We're going to let delta t be t, capital T, which is what is the symbol for the period of rotation. Okay, so it goes the time to go once in a complete circle. And our final equation then is when we cancel out one of the r's from the numerator, so when we expand this square, we get 4 pi squared r squared over r. One of the r's cancels out, so you get 4 pi squared r over t squared. That's version number 2 of the equation. period is the time per rotation. Okay, so if anything moving in a cyclical nature, or like a piston moving up and down, T would be the time for one down and up. Yeah, that's right. That's right. Okay. Guys, I hate to do this to you, but I got a third version of this equation that you have to know.
Do you really hate this?
I do actually. I wish that it was more simple, but what you're going to walk away from this lesson is 3 equations. Okay, that's about it. But they all mean the same. They all calculate the same thing. Okay, now we're not going to do this. Well, this is the same example, question 4.
Oh, okay.
Okay, so we've got version 2, and now we have to see the relationship between frequency and period. They're just reciprocals of each other. Right? Frequency is the number of revolutions per over a time period. Okay, number of seconds per second. That's the definition of hertz. And everybody's who has a computer is familiar with hertz. Processors operate in gigahertz. You get usually hard drives are RPM. Your well, you get your front side bus speed as well as in megahertz. Anyways, cycles per second, that's what we mean by hertz. Radio frequencies are in hertz as well, right? You can get 102.1, that's in megahertz. But the period is the time divided by number of revolutions. How long does one revolution actually take? Okay, and those two terms are just reciprocal values of each other. So knowing that, we can express centripetal acceleration the third way using frequency instead of period. Okay, so we're taking that t squared in the denominator, making it f squared in the numerator. Okay. So 4 pi squared r f squared. Number 3. The only other thing I want to do with you is get one actual example done on the board. One actual example. Okay, we're going to do question number 3. We're going to go backwards. I know, I'm sorry guys. I know it's a long lesson. For a Friday especially. You've been a fantastic audience. Stay with me for 5 more minutes. We'll get through one example. Michael's right now snoozing. Michael, wake up! Wake up!
He's got his headphones on.
What? Mom, it's not Monday yet, is it? Yeah, let's go. Alright. An astronaut rotates at the end of a test machine whose arm has a length of 10 meters as shown in figure 8.14. If the acceleration she experiences must not exceed 5 Gs, what's the maximum number of revolutions per minute of the arm? Oh. So we've got the maximum centripetal acceleration. We've got the radius length. 5 Gs is literally 5 times 10, our gravitational constant, 10 meters per second squared.
The textbook wants us to use that.
Wants us to use what?
10.
Yeah, that's why I use 10. Yeah, instead of 9.81. 10 meters per second squared, yeah. Oh, this is 10 meters. Yeah. And so now we just gotta solve for F, maximum frequency. Yeah, so we use equation number 3. No, 5 Gs. 5 Gs worth of acceleration.
Oh, big capital.
Meaning 5 times the...
Big capital.
Nope, Gs is lowercase.
Times 10.
Yeah. So rearrange this for F. And plug in the values. Okay, 50 divided by...
One decimal.
But the Americans that write the book wanted it in RPM. Because we're motorheads. American muscle. Everything's in RPM. So we got to multiply it by 60 to get the number of cycles per second. 21. Yeah, but if you're in a going like that's every 2 seconds you're going once around, you're being spun once around in a 3 seconds. That's right. Yeah, every 3 seconds you're going once around in a huge path. That'll put you in the puke bucket real quick. Oh, maybe not you, Josh, because you're like pilot in training.
No, but I mean, I'm just saying, I'm just thinking of the car, 21 RPM is ridiculously slow. But
Oh, a car would stall. You couldn't idle that low. You idle at 800.
That's what I mean. I
Yeah.
just made the joke, my car goes 10,000.
Yeah.
8,000.
It could get up there maybe for. Oh no, the governor would keep it. The electronics wouldn't let it do it. All right, Michael, that's a 45-minute lesson. Oh my God. Sorry.
Good luck.
We'll see you when you come back.